So the method of Lagrange multipliers is really amazing and powerful once you see it today, because you can use it to find maximums or minimums for functions of more than two variables, like three variables, maybe even four variables. You can go nuts, and you don't need to perform a d-test. So I'm going to go over the method of Lagrange multipliers today. I do have a little bit different approach than any textbook because I learned this from Dr. Vallone, may he rest in peace, of blessed memory, a professor at San Diego State. So he has a little bit different approach, but it ends up being essentially the same thing. So I'll show you where the two connect, the two ideas. So he has a cool approach, I think, and I think you'll enjoy it. So when can you use Lagrange? You can't use it every time you feel like it. It has to be the type of problem where when you're trying to find your max or your min, it has to have a constraint. So, well, what's a constraint? I don't know what you're talking about. So let's take a look at the last two problems that I went over last week when we were using the d-test to find maximums and minimums. And there were two quickie word problems I did near the end there that pretty much will give you an idea of when you can use Lagrange and when you can't. So notice example 10 that we did last week where we were trying to maximize a volume where length times width times height of a rectangular box, and we were given a constraint. Well, what was the constraint? The constraint was the other vertex of the box had to lie in a plane. And so they gave us a plane equation. Well, that plane equation, 6x plus 4y plus 3z equals 24, is a constraint. And we used the constraint in order to solve it for z, so we were able to reduce our volume formula into a function of two variables instead of three. Because when I taught you how to use the d-test, we went over how to use it where it was functions of two variables. There is a way to use d-test with functions of more than two variables, but you have a determinant that's a 3 by 3, and it's a little bit of a nightmare, so I'm not going to go over it. If you want to talk to me at office hours, I'll be happy to show you that. But it had to be reduced to a function of two variables in order for us to proceed. But this would have been a perfect candidate, this example 10, for Lagrange multipliers. In fact, we're going to do this same problem over again, all over again, in my lecture for Lagrange, using Lagrange instead of the way we did it last week. Now, example 11 that I briefly went over, I didn't have time to do the whole thing, but this example would be an example where you could not use Lagrange at all. It's not a candidate. Well, why not? Well, because we're trying to, in this case, maximize this quantity, which happens to be profit, but there's no constraint equation. Like there's nothing else. It's like just, optimize it. So this is not a candidate for Lagrange. Well, how would you do it? Well, you'd have to do it the way that we went over, which is find the critical points and then perform the d-test, the d-test, also known as second partials. So that is a little look-see into when it's okay to use Lagrange. So let's take a look at a little bit of review. So far, what have we done? We've found relative extrema for a function of two variables where df dx and df dy were simultaneously set equal to 0. And that's how we found the critical points. And then we used the d-test. Fine. So the difference with that and Lagrange is Lagrange, you already know there's going to be a max or a min or maybe both, so you don't use your d-test at all. Okay. So if you're given a function of two or three variables, and I'm going to start with a function of three variables for the first few examples, and a constraint, and this is what you need in order to do Lagrange. If you don't have a constraint, you don't have any possibility of using Lagrange. Okay, so let's take a look at an example that maybe even looks like one of the examples you did in your homeworks over the weekend. So let's say you're given 1,000 square feet of material and you want to make a rectangular box out of this material. Find the dimensions of this box that's going to make the volume a max. So we're trying to maximize volume. So if you had some rectangular box like so, and you had a width, a length, and a height, we'll just call them X, Y, Z. You can call them W, L, H if you want to. Doesn't matter what the variables. Yes, we are skipping that, and I mentioned that last week, Nicholas. No absolutes. Okay. Um, so the quantity to be optimized, in this case maximized, is a volume equation. So volume is equal to x times y times z, width times length times height. Okay. Uh, well, because we don't know Lagrange yet, if I gave this problem to you on the quiz that was due today, how would you do it? How would you know, this is a function of 3 variables. First of all, you got a problem.
All right, so
I'll give you a hint.
Oh, you just find the surface area.
Yeah, the surface area is given, and that's your constraint. You're constrained because you have no more than 1,000 square feet of material. That's a constraint. So your surface area is 1,000 square feet. Well, what's the surface area of a rectangular box here? And we went over this in lecture. We'll call it big S. That's pretty typical for mathematicians to call surface area big S. And remember, like if you look at the bottom, you know, which is x times y, there's 2 of them because you have a bottom and a top. And then like this side right here has area x times z, but there's 2 of them, a front and a back. And then right here, this area is yz, but there's 2 of them because you got the 2 opposing faces. Okay, so there's your surface area, but this is equal to 1,000. So this is your constraint. Now, what do? Well, you use your constraint equation to solve for one of the variables. Traditionally, we solve it for z. So we'll use that to reduce the quantity to be optimized, which in this problem is the volume. We'll use it to reduce that function to a function of 2 variables. So when you look at this surface area, okay, so here's the equation to be optimized. I'm going to keep anything with a z on one side of the equation, and I'll move the 2xy to the other side of the equation. This is pretty standard fare. And then I'll factor out a z from the left-hand side. I'm trying to solve for z. That's why I'm doing all this. And then divide both sides by the 2x plus 2y. And then z is looking like this. Now, one thing I'm going to do is, you could be done. I'm going to just reduce it a little bit. Like if I factor out a 2 from both the numerator and the denominator, I can make this look a little more simplified. So the 2's cancel. So what am I saying? Z looks like this. Oh, so then your volume function, which is the quantity that you would do the calculus on, would be x times y times z, but z is 500 minus xy all over x plus y. And so if we were doing this problem with last week's knowledge, we would then go get vx, set it equal to 0, we'd get vy equal to 0, and we'd get the critical point or points, depending on the problem. And I hope that you can see that this is going to be a little bit of a pain in the rear end. Well, how come? Well, do you notice that with this function, that in order to get those first partials, you would need to use the quotient rule both times? A little bit messy. Could be done, but it's going to be messy. And then, of course, getting vxx, vyy, and vxy is probably going to be even more of a nightmare, because you'll definitely have to use the quotient rule for those. So it's starting to look pretty involved. So we could finish the problem using our previous knowledge, but let's stop here and ask ourselves a question or two. Why do we always have to solve for z? How come he's the one that we always have to have dependent on x and y? I mean, could it be where we go, oh, you know, how come we're always solving for z? No, x, y, z is not equal to 1,000, Adriana. I'm sorry. No, that's incorrect. They're telling us that the square feet here. The fact that that's square feet and not cubic feet tells me it's not a volume. Okay, Adriana, be careful. You gotta be very careful. Check your units. So the question is, why do we always have z dependent on x's and y's? Like if you look here, we said, well, we're going to solve for z and then plug that into our volume function. Okay, fine. And then we'll have a function of x and y only. Great. But, you know, are we like prejudiced against z, you know, where we always make him dependent on the x and y? Why couldn't we solve for x instead? And then we'd have a function where our volume would be a function of y's and z's only, which we could do. Now, there's some literature out there, and I have some articles where it turns out when you solve for z and have him dependent on the x and y, you get the wrong answer. Yeah, David Widmer. So it turns out it's bad. So this is like not fair. So David Witter here, if you look, you'll get the wrong answer. So Lagrange, you never end up getting wrong answers because you never have to worry about solving one of the variables for the other guys. Okay, fine. So what does Lagrange tell you to do? Lagrange tells us to introduce a new variable into the whole conversation. In addition to x's, y's, and z's, which are already in the conversation, we're going to introduce this new variable lambda, which is a Greek letter, the Greek letter for L kind of standing for Lagrange. So this is the Lagrange multiplier. Well, how is introducing another variable into the conversation going to help us? We already have enough of them, x's, y's, and z's. Now we're going to get a fourth one? Yes. But it's going to turn out, it's going to make our life easier. So here's what the Lagrange method has us do. Instead of extremizing, and I know that's not a real word, but Arnie used to use it, the function of fxyz, which for us right now is the volume formula, subject to the constraint, and our constraint right now is the surface area. But you're going to have some constraint equation. We're going to create a brand new function, and this is not in the text. This is the way I'm teaching it to you, okay? And I'd appreciate it if you do it my way, okay? And you'll thank me later if you do it my approach. I know some of you totally ignore me, and you know who you are. Like I teach you something in my class, and I say, I'd appreciate it if you do it this way. And then you go off and hit the show an example button on my math lab, and you do it that way, and then you totally ignore what I'm saying. Well, ignore at your own peril. I try to show you the easiest way to tackle this. So I'm encouraging you to use my approach.
Sorry, Professor, one last time. Why is it not okay to have the z variable not independent? I'm sorry, not dependent.
Well, sometimes you get the wrong answer.
It's it? Oh, it's okay.
Sometimes you actually, when you solve z in terms of x's and y's and plug that back in, David, you actually end up with a totally wrong answer. I'm not kidding. Like, it's bad. And you don't want wrong answers, do you, David? Of course not.
I mean, no.
No. So Dominic, you can thank me now and tonight and tomorrow and yesterday and
Thank you.
yeah. So do it at your own peril. So you're going to extremize or optimize essentially a brand new function of 4 variables. Oh my God, that looks horrible. Don't worry, it's going to be cool. So the way you're going to form this big old function L is you're going to take the formula or equation of the quantity you're trying to optimize. It could be maximize or minimize depending on the problem, or both, as you'll see, minus lambda multiplied by your constraint. Now, your constraint has to be written a very special way. You have to rewrite it where you get everything on one side and 0 on the other. And then you stick your big G in here. Now, so in our box problem, the big F for us is the volume function. So for us, the volume is a function of 3 variables, and it's x times y times z, width times length times height. And the constraint equation, so the big G for us, is the surface area. So if you look back here when we were trying to do this box problem, this right here is your surface area. This is your constraint. And if you don't mind, I'm going to divide both sides of that equation by 2, just to reduce it a little bit, although you could use that one also, it's fine. But if I divide both sides of the equation by 2 and then get everything on one side and 0 on the other, then this is what my constraint equation looks like. Now, with Lagrange, you don't have to solve for z and get it in terms of the other guys, okay? You don't. What you're going to do is you're going to optimize big L. So this is the function that you're going to focus your eyeballs on. And you're going to basically get all of his partials and set all of his partials equal to 0. And you'll get a huge system of equations, which most of the time is very nonlinear, as you will see. So, because this is a function of 4 variables, how many first partials do you think you're going to have total?
4.
4. You bet. So, when you look at getting your first partial with respect to x, which you could also use this notation, the differential notation, your choice, I don't care. You'll notice since your big function here looks like this, you'll, big F, you'll take his partial with respect to x, minus, and then lambda is a variable, but when you're taking the partial with respect to x, you're going to hold y, z, and lambda constant. So lambda is a constant multiple, and you'll just multiply that by the big partial of g with respect to x. And then, of course, you want to simultaneously set all these partials equal to 0. So the partial of big L with respect to y will be whatever the partial of big F is with respect to y, minus lambda times the partial of g with respect to y. And similar for taking the partials with respect to z here. Now this one's a little weird because the lambda we just introduced, so it may be a little tricky for you to think about lambda as being an actual variable. So when you're taking the partial with respect to lambda, you're going to hold x's, y's, and z's constant. X, y, and z all looks like a pure number. So what is the derivative of big F with respect to lambda, knowing that big F only has x's, y's, and z's in it? Anybody want to?
0.
0. And then the derivative of negative lambda times the gxyz, well, this gxyz just looks like a constant multiplying with your lambda. So the partial with respect to lambda is just going to be negative g. And then, of course, you'll set that equal to 0. Now, if you'll notice this equation right here, if you multiply both sides by -1, it's exactly the same as your constraint. And that always ends up being the case where your L lambda is your constraint. So you go, well, I set it equal to 0. No, okay. You still need it because it's still part of your system of nonlinear equations here. So this is a system of nonlinear equations, and you go solve it. And that's sometimes the hard part. Like, I won't lie, that's going to be problematic for a lot of people because that's the tough nut part of these types of problems. Now, when you solve this system, and I'm going to show you some techniques for solving it, you will get a critical point or critical points, but you never have to do the d-test on those critical points. Well, how do you know which one's the max and which one's the min? Because we don't worry about saddle points at all when we do Lagrange. Nobody cares. The way you'll tell who's a max and who's a min, and you're not going to like this answer because it's kind of primitive. You plug it into the original guy and see who gives a high value and who gives a low value. Yep, that's how you're going to figure out if it's a max or a min. I know. Trial and error. Okay, so Dr. Arnold Malone of blessed memory used to say that this lambda is an angel variable. You can think of this angel coming down from heaven and helping us out a little bit. And then after you're all done, the lambda goes away and goes back to heaven. And okay, bye, angel. Thanks for the help. So because usually you never have to solve for lambda, or you don't at the very end of your problem. Nobody really cares what lambda is, except our economists and physicists brethren. A lot of times they care about the actual value of lambda at the end of the problem. Economists like to use it for weird purposes and whatever. So you do have to be sure that your functions that you're trying to find a max or min of, they don't have gradients that are equal to the zero vector, because that means like fx, fy, and fz would all be zero, and that's not interesting. So we want to make sure that the gradient of f is not equal to zero, and the gradient of g not equal to zero. And if you haven't seen the grad notation, I'm going to introduce it to you now. It doesn't show up in Briggs, but a lot of times physicists as well as mathematicians will refer to a grad. It's the same as del F. It's the same. It's just different notation. Here we have del G. So we want our functions to be regular. Okay. So now what? What I want you to notice in these equations here, like just look at one of them. If you rearranged the first one and you added lambda gx to both sides, your first equation would have this flavor, fx equals lambda gx. Similarly, if you did that to the second equation and the third equation, you'd have these three equations instead of the way I set it up. So if you're going to read Briggs or any other calculus books, a lot of times what they'll do is they'll say, hey, when you're using Lagrange, you're going to have your del F equal to lambda del G. So they're basically setting, and this little f is the same as our big F with my approach. And their little g is the same as my big G with my approach. So they're just basically saying that this gradient is equal to a multiple of this. That's what Lagrange multiplier is, the multiple of the gradient for the constraint function. Okay?
That's a
So,
quick question.
sure.
Okay, this probably isn't relevant to like finding the actual like process of doing Lagrange, but like just to be sure, lambda isn't really referring to a specific geometric measurement that occurs as a result of like the existence of a said shape, but it's a
No,
dummy variable composed of like various other elements of that shape.
it's not a dummy variable, as you will soon find out. Okay?
Okay.
Back to my problem. When I derive it, you'll see why it's there. Okay?
Okay.
You'll totally understand geometrically what the heck it is. But for now, be patient. So back to the problem, our time for hand-to-hand combat, as Dr. Vallone would say. So we're going to finish the problem. What are we trying to maximize? You're trying to maximize the volume, which for us, if I call it big fxyz, is the function x times y times z, length times width times height for this box problem. And the constraint, which I'm calling big G, function of three variables, is the surface area constraint, because we only had 1,000 square feet of material. So I reduced that surface area equation a little bit because I divided both sides of it. Oops, that's minus 500, sorry. Because I divided both sides of it by 2. So I guess I can't use my eraser. No, I did. So minus 500, and you always want to get your constraint where you have everything on one side and 0 on the other. Okay, so the Lagrangian, and this is just a repeat of what we did on a previous page at the risk of being redundant, but now I'm going to actually plug in the F that we have and the G that we have. So this is the volume minus lambda, that's our Lagrange multiplier, multiplied by the constraint, xy plus yz plus xz minus 500. Okay. So now we're going to find all four partials of this big L, this big Lagrangian function. So because we're basically optimizing the big L in this approach that I'm showing you, which is not in the text. But I'd really appreciate it if you would follow it, because it's great. So I'm going to get Lx, Ly, Lz, L lambda, all four partials. Okay, let's hit it. So when I find the partial of big L with respect to x, what is the first term's derivative with respect to x? Quick.
Z.
Minus lambda times whatever the derivative is inside parentheses with respect to x. which is what? We're differentiating with respect to x.
So
I think we're
y-
going to
y
have a
plus z.
Plus C.
y plus a z, yeah. And let's see, why is my computer so slow? I don't know. Set that equal to 0. Now let's find the partial with respect to y. So the derivative of xyz with respect to y is xz, and minus lambda times the derivative of what's inside parentheses with respect to y. I get x plus z. Set that equal to 0. Partial with respect to z. Derivative of xyz with respect to z is xy, and the rest of it is minus lambda times, I think we're going to get x plus y. And then L lambda, which is the derivative of big L with respect to lambda, keep in mind lambda is a variable. So you're going to hold x, y, and z constant. So the derivative of x, y, z with respect to lambda is 0. And then you're going to have minus. And this mess right here in parentheses looks like a multiple of lambda. And so that multiple is the derivative of lambda. And then you set this whole thing equal to 0. And I hope you can see if you rearrange this equation and you multiply both sides by -1, this is indeed the same as your constraint equation. Same thing. And that's always going to happen. Okay, now, how do you do the algebra for this? Because this is where it gets a little tricky. All right. So I'm going to show you one technique that the book isn't really into my technique. But again, for those of you who listen to me, I'm trying to save you from pain, and I'm trying to save you from agony, unless you love pain, in which case, go ahead and do it the way the book or the view an example button shows you. Good luck. But for those of you who like peace, you'll find that my way is awesome. And this is one approach. It may not work all the time because I'm going to do some other flavors. I may not get to it today, but for sure by Wednesday when I finish out this section. So I show you all the different ways. But this technique, if it does work, it's wonderful. Okay, so the technique, I'm going to just I'm going to talk you through it, then I'm going to walk you through it. I'm going to solve for lambda 3 times. What? Yeah, using Lx, Ly, and Lz. I'm going to take each of those individual equations and solve them separately for lambda. Lambda, and I'll call lambda is lambda, but I'll call it like lambda 1, lambda 2, lambda 3. And then I'll start setting my lambdas equal to each other. Well, why the heck would you want to do that? The goal is to try to get the variable, 2 of the variables in terms of the third one, and you kind of could pick which one that is your favorite. And then once you get everybody in terms of that one, I'm going to try to get everybody in terms of x. So I'm going to let x alone, but then try to get y in terms of x and z in terms of x, and then plug all that stuff into my constraint, and then I can at least nail down what the heck x is. And then I'll be able to easily find the other 2 guys, the y and the z, and then I'll determine my critical point or points, and then I'll figure out if the point or points is a max or min using the primitive way of plugging it back into the original function. Okay. So if you look here, if you look at this function here, so this is my first equation here. I'll just call it number 1. If I try to solve that for lambda, so what the heck am I going to get there? If I add lambda and the y plus z quantity to both sides, I end up with that. And then if I divide both sides by y plus c, I get lambda is equal to yz over y plus c. Let's call that lambda 1, even though there's no such thing as lambda 1 or, whatever. I'm just going to sort of denote that just to distinguish it from the other 2. So the next equation here is the partial with respect to y. I call that number 2. And again, we're going to solve for lambda. So if I add lambda x plus z to both sides of the equation and then divide both sides by x plus z, I'll get lambda again. Okay, fine. And lambda is lambda, but I'll just sort of denote it lambda 2, just to distinguish it from my lambda 1. And then finally, the last partial with respect to z, and I'm going to ignore the lambda partial with respect to, or excuse me, L with respect to lambda, because he'll come into the situation, but kind of near the end. So I got my lambda 2. Now, when I solve for lambda for the last partial there with respect to variables, I'll have xy equals lambda x plus y, and then divide both sides by x plus y, and I'll get lambda 3. Fine. So now I got 3 different lambdas, but really they're the same. So this is where you're going to set one lambda equal to another. So like, what if I set the first guy equal to the second guy? Okay, fine. So what am I saying? Lambda has to be equal to itself. So if I go lambda 1 has to equal lambda 2, because they're really not different lambdas. They're really just lambda. So yz over y plus z had better be equal to xz over x plus z. Really? Now what? That looks like a hot mess. Your goal right now is to try to get one of the variables in terms of one that you pick. And like I said, I'm going to try to get everybody in terms of x's. So if you'll notice, this is a fraction equal to a fraction. So if I multiply both sides by the LCD, I can clear fractions, which is y plus z times x plus z, and then reduce. And then on the left, after reducing, I'll have yz times the quantity x plus z. And that had better be equal to the other side of the equation, which is xz times y plus z. Now I'm going to do something that traditionally is illegal in mathematics. I'm going to divide both sides by z. Why is that usually illegal in math? Somebody tell me.
You can be equal to 0.
Yeah, you could be in danger of division by 0, which is not okay when you're trying to solve an equation. But we're going to assume that z is not equal to 0 here, because, and we can easily do that for this type of problem because of the fact that we're doing a rectangular box and z is supposed to be the height of our box. And certainly I hope you would agree that maximizing the volume would not occur if we let the height of our rectangular box be 0. So we're going to go, hey, we don't even care about that, so that z won't be 0. So then when we reduce to lowest terms, we have y times x plus c is equal to x times y plus c. And now I'm going to distribute to get rid of parentheses on both sides of the equation. So I have xy plus yz on the left, and that is supposed to equal xy plus xz on the right. And then simply subtract xy from both sides, so they're gone. And then I have yz is equal to xz. Yeah? Is everybody okay with this?
Yeah, sure.
Sure.
Yeah.
Hang on a second, because I'm just looking at something. Oh, I see what I did. Okay, and then I'm going to do something again that's illegal. Oh no, really? Yeah, I'm going to divide both sides by z again. Again, z is not 0, remember? We're cool. And so y is equal to x. So save this for later. That's not the answer to anything. That's just going to be y related to x. So you got that. Save that for later. And then what? Well, now I'd like to get z in terms of x. So I kind of look at all these lambdas I have here. And how about if I set number 1 lambda equal to the number 3 lambda? Yeah, okay, I think that's going to help me get my z. So I go, okay, yz over y plus z has to equal the 3rd lambda that I got, which is xy over x plus y. And then and multiplying both sides of the equation by the LCD. Another quick way to do this is you could do something called
Uh-oh.
So it wasn't just me, right?
Okay. I got DC'd as well, so like, I'm not. I don't know.
Same.
I thought
Thank
I was
God.
kicked
Oh no,
for
it
being.
was just Zoom.
I thought I was kicked for being too bad at math, but then I don't know. Like everyone, you know.
No, Cox has been real bad right now. I just
No,
got
sir. Holy fuck. Oh wait, no. Okay. The meeting's still
Yeah,
being
good
recorded.
save, good
Watch
save.
my language. Yeah. Okay.
Hey, can you guys hear me now?
Yeah.
Yes.
Yeah.
Did I crap out for a while there?
Yeah.
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 Okay, sorry about that. Well, you know, internet, wonky internet is my middle name. So what did you miss here? Did you miss me doing setting 1 equal to 3?
something.
No,
about
we
the
just
valuing
started setting
functions.
up 1 to equal to.
Okay. So are you okay right now then?
Yeah, but we need you to screen share.
Oh, good thing. I guess it stopped screen sharing. Oh boy, that's unfortunate. Well, I had internet problems yesterday too, so this doesn't surprise me. Maybe I should drive over to the Southwestern College in their parking lot. Okay, so you can cross multiply, and that's not because your 5th grade teacher told you so. You're essentially multiplying by the LCD. So if I do that, and I'm really lagging on my, I don't know what's going on with my, I have no idea. Okay, so I'm going to, that was supposed to be YZ. Now I'm going to do this a little bit differently. I'm going to distribute right now. And so what do I get? I get XYZ plus Y squared Z. That's equal to XY squared plus XYZ. I'm doing this a little bit differently from the way I just did it, but it's going to end up to the same thing. So please try not to freak out. Okay? Try not to freak. So notice that XYZ is a term on both sides of the equation. So simply subtract XYZ from both sides. Okay, fine. Then I have Y squared Z is equal to XY squared. Okay. Well, assuming that Y is not 0, divide both sides by Y squared. So it'll be legal. And then you'll get Z in terms of X. Okay, fantastic. Good news now, folks. This is the part where we're getting close. You got both both Y and Z in terms of X's. Now, are they always going to be exactly the same? No, this is a super easy problem that I'll never give to you on a quiz or a midterm, okay? I give way harder problems. I'm only starting with an easy one to boost your self-esteem. So you're going to substitute both of these into the constraint. What was the constraint again? I forgot. That was, for us, the surface area function. So if you look at the surface area function, you know, the equation that is, you can either do it, plug it into the original one that we did, which is right here. This is the surface area. You know, this is the reduced version. And so I hope you see that if you substitute both Z and Y with X's, both of them are the same as X, what is your constraint equation going to look like? I claim it's going to look like X squared plus X squared plus X squared equals 500. Well, then what? Well, then 3x squared is equal to 500 after we combine like terms. And then what? Well, I'm trying to solve for X here. Okay, people? So I'm going to divide both sides by 3. So I have X squared is equal to 500 thirds. Ooh, that's kind of gross. Yeah, it is. And then you're going to take the square root of both sides. And what do you always have to remember when you square root both sides of an equation?
Plus
You
or
have a plus
minus.
and a minus.
You better remember your plus or minus. Do you think that I'm going to test you on this in some way, shape, or form on a future exam?
Oh, yeah.
You bet your
Yes.
sweet bippy. You bet your sweet bippy. Now, why can I safely ignore the negative for this problem, not for every single Lagrange problem you do?
The
Why is
rectangle isn't that
Negative
long.
surface area.
Yeah, because our real life, real world problem, our X happens to be the width. It's representing the width of a rectangular box. And on this planet, at least, you cannot have negative widths. However, I do want to say on regular Lagrange multiplier problems where it doesn't, you know, you're just doing, maximize this beautiful expression with this constraint, and it's not applying any real world situation where you're limited to positives or, you know, and not negative lengths, then you take both. You take both the plus and the minus. That would mean you have, in this case, 2 critical points and not just one. And one's probably going to give you the max and the other one's going to give you the min. Okay, now here, I'm going to simplify a little bit because I happen to know that 500 is the same as 100 times 5. I'm just trying to make this look a little bit prettier. And so when I simplify the radical, and again, this is just for prettiness here. It's going to look like 10, and that square root of 5 is still there underneath the radical. 10 square root of 5/3. And this is in feet, and units do count. Now, what about the y and the z? Well, we already figured out for this problem that y and z are exactly the same as x. Okay, so what are we saying? We're saying z equals y equals x. So this box is really a cube. So to maximize the volume of this box with the given surface area, you're going to have a cube, and then the actual max volume, and then you're just going to go, okay, what is the actual max volume? Well, it's going to be, you know, x times y times z, which is basically 10 times square root of 5/3 cubed, and that's going to be some ugly looking number, trust me. After you do all the multiplication, it's going to be 500 times the square root of 500 over 3 square root of 3, and which, if you reduce it even further to make it look prettier, 5,000 square root of 5 over 3 square root of 3 feet cubed. Okay, so there, and a lot of times these problems do end up with weird answers with all sorts of radicals everywhere. So don't be alarmed. Yeah, like, oh, that must be wrong. I should be getting a whole number. No, most oftentimes you don't. Sometimes you do, but here, no. You get a really weird dimensions, and you get really weird volumes. So we're done with this problem, and congratulations, you just saw your first Lagrange multiplier method to find the max. So let's just recap. The way you do it, at least the way I'm approaching it, is you form what Arnie used to call the big mother of a function, this thing called the Lagrangian function, which is your function to be optimized minus lambda, that's your angel from heaven multiplier, times your constraint. You find the partials for that Lagrangian function, set them all equal to 0, and try to solve the system of nonlinear equations. And one approach is to solve for lambda 3 times and set the lambdas equal to each other in order to get a couple of your variables in terms of the other guy. Okay? So what makes the method of Lagrange multipliers work? Or as Arnie used to say, what was Lagrange smoking? So David, since you were kind of speculating with some conjecture on what it was, I'm going to appoint you the colonel. We're going to go into space. Are you ready?
No, I mean, yes.
Colonel David. So I'm going to do the derivation, and you're not going to see this in any text or any video. Okay, this is how Arnie would roll. So suppose this F, that's the quantity to be maximized or minimized, instead of volume like we just did the last problem, what if it represents temperature at any point x, y, z in space? Woo, doo, 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 doo. So then we're going to imagine an astronaut flying in space. That's Colonel David here. Oh yeah, Colonel David is going to take you on a trip to the moon or wherever, maybe Mars. So
Your
then imagine, where do you think you want to go, David, huh? Yeah, any ideas?
Home.
Oh, so what planet would that be?
It's not in the solar system. It will be 5 times over the current terrestrial expenditure. We will bankrupt ourselves several times over. We will induce a status of financial chaos that will stretch for the next 10,000 years.
Stop being so dramatic. The Kelso Empire already destroyed it.
I am kicking you out of this. I am kicking you out of the spaceship, Nick. I hope you're quite. I hope you hate oxygen.
Does anybody ever watch that sci-fi show called The Expanse? Am I the only one? I guess
I've never heard. What is it?
Go Google it up. It's on
Okay.
hiatus right now, but it'll be coming back. It's an amazing. I'm not even really into TV much, but this is awesome. Anyway, so they did kill this one guy who was the Belter captain, and the way they killed him is they pushed him out into space, and then you die immediately because you can't breathe out there. So, and they just showed his body floating in space. It was sad because he was a fun character. Anyway. So let's say Colonel David wants to land on planet X. Fine. Planet X's surface is represented by this equation, big G x, y, z equals a constant, which you recall is the way you can represent a level surface. And even more so, we're going to get everything on one side. So this is just some constant. it could be 0. But if it isn't, then get everything on, get that constant on the left so that you have it equal to 0. So this is your level surface. So this is your constraint surface. So this whole situation that I'm setting up here, where David is our kernel, he lives on this planet, which is represented by this level surface. And that's a constraint surface. So we're going to look at the temperature on David's planet. And the temperature function is big F. And we're going to look to see if there's a max temperature or a minimum temperature or whatever. So let's say that the kernel records the temperature after he looks around. He's hunting on the planet to find the point of greatest temp. And let's say at point P on the surface of the planet, he finds, ooh, he's got what looks like might be a max. So here's his little recording device where temperature is going this way and time T is going this way. So if he's recording temperature, let's say at a certain time, he's like, oh, woo, right there, we have a max. At point P, we have a max temp. Oh man, that's pretty cool. Well, maybe David, Colonel David isn't convinced, and he keeps roving around on his little Mars rover. Let me go see some other places where there may be a temperature. So like if this were his surface, let's say right here at point P, he went through that point on one path. We'll call that curve 1. But let's say he chose a different path, and on a different path, he's, cruising around the planet. And let's say on this curve right here, we'll call it C2. Let's say he still notices that at point P, we've got a max temp. So on the recording device here, you got your temp, you got time, and at some time T here, he's like, hey, I still have this max at this point P. So now it's like, wow, this is kind of weird. So this is the C2, this is the C1. So you're comparing these two recordings here, and both of them you seem to always get at point P, you get this max. So now we're going to look at the temperature as a function of time. And what I love about this derivation is we're going to bring the chain rule into it. So here we have the function, this is your temp function. And the temp function, remember, is a function of x, y, and z. That's the point you are in space, could be on a planet. And now we're going to talk about x, y, and z being functions of time t. So we're going to ask, what is the temperature as a function of time t? So if you take one of those curves and have it represented by a vector valued function, r of t equals x of t, y of t, z of t, that's your position vector, and you plug that position vector into your big mother of a function here, big mother of a function of time, f, x, y, z, you're going to get f evaluated at x of t, y of t, z of t. So Arnie would say one big mother function of time. And from first semester calculus, when do you have a max at a point? Isn't that when the derivative is equal to 0? So in other words, here at time t, where we keep getting this max temperature here at point P, what can we say there? Well, f prime of t has to equal 0. That's what we're saying. So now the chain rule of several variables. So here's where we go, okay, f prime, and if we use the differential notation, that's the same as df dt. And from a couple weeks ago when we did the chain rule, I hope you remember because it's going to be on the midterm, df dx times dx dt plus df dy times dy dt plus df dz times dz dt. Oh man, not that again. Oh yeah. And because f prime is equal to 0, we're basically saying this is equal to 0. Now here's the part where I want you to notice that it looks like a dot product, doesn't it? Something times something plus something times something. This is a dot product of two vectors. What are the two vectors that this left-hand side looks like it's taking a dot product of?
That's going to be, well, one of them is r prime of t, right?
Yes, very good, which is a tangent vector to the curve. Excellent, George. Good. And what is this guy? Doesn't this guy look familiar to you?
Isn't that just the gradient?
Yes, that's the gradient of big F. So what are we saying? The gradient of big F, and you take it to dot product with the tangent vector to any curve, it turns out, and you get 0. Now, what do you guys know from the first week of class? When you have the dot product of two vectors equal to 0, what's the relationship to?
They're orthogonal. Mhm.
Yeah,
Yeah,
so
whatever they
this is
said.
the dot product, and it means that del F and R prime here, it turns out that the gradient is always perpendicular or orthogonal to the tangent vector. Okay, that's R prime. When your kernel, that'd be kernel David, is located on the constraint surface. But wait a minute. We learned in a previous section that the gradient for constraint surface is always orthogonal to level surfaces. That was a theorem from that whole section. So in other words, the gradient for the G function, that's the planet, is also be orthogonal to its own surface. In fact, that's how we would find a tangent plane, is we'd go get the gradient to every tangent vector also. So in case you're wondering here, if I'm going to draw a picture, like here's your planet, here's point P, you can draw any curve through there that you want. And del F is always punching outward because any of those tangent vectors, are going to be orthogonal to del F. But it turns out that del G is also orthogonal to every tangent vector. So here's del G. So what can we say about del F and del G?
They're the same line, or rather, the very linear. Jesus
They're
Christ?
multiples of each other.
They're
Yeah, that thing.
parallel vectors. Yeah, so one is a multiple of the other, right? From the first week of class, one must be a multiple of the other. Write all this down. This is like key, people. So del F is a multiple of del G. That's like amazing. Like right now, you should be saying, wow. So when you have two vectors that are multiples of each other from our discussion from 7 weeks ago, you would set them almost equal to each other. You'd say, well, del F, that vector is some multiple C times the gradient of G, del G. But folks, this is for you, David. Instead of C, we use the Lagrangian, the Lagrange multiplier. That's all it is.
Oh.
You're saying that the two gradients are parallel. Cool. And one's a multiple of the other. Cool. So what's cool is instead of C, we use lambda. That's our variable that's representing, the multiple. Isn't that cool?
Oh, snap.
That
Okay.
is
Yeah, it's kinda cool.
awesome.
Really
Awesome
quickly,
stuff.
if you can correct me on my like nomenclature, does that mean that how to put this? Lambda doesn't always have to equal a constant, right? Or is it
No,
always
it
a
is.
constant?
It is. It
Oh, it is
basically
absolutely a
is.
constant. Okay.
Mhm.
All right. So the gradient of G
It's
is a linear
a variable.
Okay.
So a variable represents a number, right?
Mhm.
It's like, every time you see the letter X, whether it's an equation or what a function, doesn't it represent a constant, some constant
Yeah.
that could be variable?
Right.
So
Okay.
this is just some constant. And what is the constant? Well, that depends on the problem. Now, remember earlier, about a half an hour ago, I mentioned that only our physicist brethren and our economist brethren actually solve for lambda at the very end of their problems because they care about it. Us mathematicians, we don't typically solve for lambda because we don't care. It's that after it helps us get our max or our min or both, we're like, hey, thanks lambda, and it goes back up to heaven, and because it's an angel from heaven that just helps us out. Okay.
Just to be sure though, could the gradient the gradient of F can be represented as a linear combination of gradient G? I hope I'm not using
No,
terminology
well,
that's
this
not
isn't
my
a
def.
linear. You're saying a vector is equal to a vector. So no, it's a linear combination, but usually linear combinations, we think of sums. There's no sum here.
Okay, never mind.
Okay, we're talking about a vector. Remember when the left-hand side is equal to the right-hand side, people? Hello?
Correct. Yes. Yes.
And you can distribute the lambda. So, the very first week of class when we were doing some fun and play with vectors, I mentioned that, hey, quality of vectors means, the left-hand side is equal to the right-hand side. And I'm having such a delay here with my Surface Pro, I don't know what to do. And so what are you saying? If the left-hand side is equal to the right-hand side, then you can simply set the components equal to each other. Is everybody with me?
Yeah. Yes.
Mhm.
Yeah.
Hello. Hi. And this is what the text has you do. I don't have you do this because essentially when I have you find the big Lagrangian function that Arnie would call the big mother of a function or whatever, you end up doing the same thing if you do it my approach, which I have you find big L, and then I found you have you do all 4 partials of big L. And so what you're essentially doing is you're doing this. So like if you look over here, when I had you finding, when I was just doing the derivation, if you look at these partials of big L, you're essentially setting each and every one of the components
Oh, I see it. Oh, wow. All
equal to lambda times the partial of the other function, the big G function. Does everybody see this, that I'm actually doing that?
Yeah.
right. Wow.
Yes.
Is it all connecting for you in your brain? I hope
great.
so.
It's created a tapestry, and it's very scary to look at.
So if you do my approach, you'll warm my heart, and I really appreciate it, okay? Or you could do what a lot of students do, and they just ignore me and do it their way and at their own peril, okay? So let's just recap everything we just did in the last hour. So here's the method of Lagrange multipliers for a function of 3 variables. And we'll do it for 2 variables also, but I like to start with the harder than the easier is like, that's a piece of cake. Okay, so what you're going to do is you're going to start off, you'll read the problem. It might even be a word problem, and they're going to give you some function that's the one that you're trying to find the max or the min for. Okay, or both. And then you'll have a constraint, and you may need to rewrite the constraint so you got everything on one side, 0 on the other. Then the max or the min, or you can find both, will occur at one of the critical numbers of the new function, big L. And big L will be a function of 4 variables, x, y, z, and lambda. And you set it up by taking the little f, although I like to call it big F, but whatever, same. Minus lambda, that's your Lagrange multiplier. It's your new variable you're introducing into the system. And you multiply the lambda with the constraint function, big G. And then you get your 4 partials, and you simultaneously set them equal to 0. And the last one is always the same as your constraint equation. The L lambda, the partial of L with respect to lambda, always ends up being the same as the constraint with a negative in front. Okay, fine. Okay, now I'm going to redo the box problem from last Friday. So remember last Friday where we had the function that we were trying to maximize the volume of a rectangular box, where the box was sitting on the ground, where the ground was like the XY plane, where one of its vertices was located at the origin, and the other one was in the plane, 6x plus 4y plus 3z. And remember, we drew a portion of the plane by finding the intercepts of the plane, and I'm just trying to draw the plane a little bit nicer here because the x-intercept was 4, the y-intercept was 6, and the z-intercept was 8. And so here's a portion of the plane. And so your box was sitting behind the plane. And you don't have to draw pictures when you're doing stuff like this, but it certainly can kind of help you if you visualize. So this vertex right here is located in the plane. So you've turned 2 vertices. And so if x is your width and y is your length and z is your height, remember so our big F is the volume, which is x, y, z, and that's who we're trying to optimize, in this case, maximize. And your constraint equation is this guy. It's constrained by it has to be in a plane. So big G, if I get everything on one side and 0 on the other, it looks like that. And so my big L function, that's the one that you're actually trying to extremize. You find his critical points. You're going to set it up where you have your big F minus lambda, that's your Lagrange multiplier, parentheses, because you're multiplying the Lagrange multiplier by your constraint. Okay, so this is the function that you're going to find 4 partial derivatives for. I know, pretty gross. And by the way, we're not going to have to do any stinking d-test here. No d-test. It will be a little bit easier than what we did on Friday. Not like total cakewalk. Like, well, after I'm all done, don't go, well, that was still time consuming. Well, yeah. But you don't have to find any second partials, which is the beauty. So when I find the first partial derivative of big L with respect to x, I'm going to get yz minus, and then lambda times, and if you look at everything inside the parentheses and differentiate with respect to x, you'll just get a 6. And then set that equal to 0. And then when I get the partial with respect to y, I'm going to get xz minus lambda times 4. When I take a derivative with respect to z, I'll get xy minus lambda times 3. Set that equal to 0. When I take the derivative with respect to lambda, I'll get negative, and then x and y and z are held constant. So this stuff in parentheses looks like a multiple of the lambda, and so set that equal to 0. And this is a system of equations, and you got to go solve the system. Yeah. And there's different ways to do it, but if you follow my lead from what I told you before, it'll work. So if I solve this for lambda, I'll get lambda equals yz over 6. I'll call that like my number 1 lambda. If I solve for lambda with the second equation, this is pretty easy here, I'll get xz over 4. So I'll call that number 2. And then if I solve for lambda a third time, I'll get xy over 3. Okay, so I have 3 different versions of lambda, but lambda is supposed to be equal to itself. Okay, so if I set the number 1 lambda equal to the number 2 lambda, okay, what do I have here? I got yz over 6 had better be equal to xz over 4. Nice. Now what? Well, if I divide out both sides by z, and I assume z isn't 0, and then multiply both sides by 6, I'll get y is equal to 6/4 x, and then I'll reduce and I'll have y is equal to 3/2 x. Save that for later, because now I have y in terms of x. I always like to try to get everybody in terms of x. You don't have to. If you want to get x and z in terms of y's, that's fine. You just want to kind of get everybody in terms of one variable, because when you plug that into the constraint, you'll have an equation of one variable. So you can get one of the variables. So that's my point. So now what? Well, let's set the number 1 lambda equal to, how about the number 3 lambda? And that'll help me get z in terms of x's. Okay, so I'm basically saying, you know, I'm saying lambda is equal to lambda when I'm doing this, in case you're not clear what I'm doing here. Yz over 6 is equal to xy over 3. Well, if I divide both sides of this equation by y, assuming y isn't 0, and then multiply both sides by 6, I'll have z is equal to 6/3 x, but if I reduce, that means that z is 2x. Okay, good news. You have y and z in terms of x's. So now what you're going to do is you're going to substitute these into your constraint equation, and that will help you to get x. Okay? So your constraint equation is the equation for the plane. So that's this guy right here. So when you plug, you let x be x, but if you plug y equals 3/2 x and z equals 2x into your constraint will look like 6x plus 4y, but y is 3/2 x, so we substitute, plus 3z, but z, we're going to substitute 2x instead. and set that whole mess to 24. There's your plane equation. And then solve this for x. So after reducing, you'll notice I'll get 6x plus 6x plus 6x equals 24. Ooh, nice. That means 18x equals 24 after combining like terms. And then solving for x, divide both sides by 18, and I can reduce this to lowest terms, and I get 4/3. So once I have x, I can easily get y, because remember, y is 3/2 x. So you'll just substitute 4/3 now for x, and then reduce this to lowest terms, and you'll get y is equal to 2. Fantastic. And then z is supposed to be 2x, which you got already. So 2 multiplied by 4/3 has us get z is equal to 8/3. So the final answer for this problem is that the dimensions of your box that will maximize your volume are 4/3 by 2 by 8/3. And then the actual max volume, you just multiply all these together, 4/3 times 2 times 8/3, and I get 64/9 cubic units, whatever that is. Okay, there's your, and this is the same answer we got on Friday. Okay, same. Better be. Okay, I'll stop there. It's been a long ride here. Questions?
When you got the lambda into the terms of other variables, or got lambda by itself, like, does it matter which ones you pick? Like, you pick number 1 and 2.
No, but you don't want to duplicate yourself. Like, let's say you set one equal to the other and you got y in terms of x, and then you set another one equal to another one and you get y in terms of x again. Well, that's not helpful.
I get it. Okay.
So you want to set them equal to each other where you're getting, not wasting time, where you get everybody in terms of the variable that you desire to get everybody related to. So it's kind of up to you. Does that help?
Yes. Thank you.
Hey,
Any
Professor, this
other
is kind of
questions? Go.
this is kind of a throwback, but like, why is it that like you can't you can't use z to solve for another side? Like you have to use something else.
Well, we're not doing that technique here at all, David. I think
Never
you
mind.
might
Oh,
be a
okay.
little bit confused. If you're using the technique without Lagrange multipliers, where you have to reduce your function to a function of 2 variables in order for you to be able to do the d-test and everything, then you're going to need to reduce that function to a function of 2 variables, and that's when we use the constraint to solve for z traditionally. But we don't have to do any of that for Lagrange. Lagrange doesn't have us solve for one or the other.
Right.
But when I'm finding the y's and z's in terms of x, that doesn't mean I'm substituting. I'm just trying to get everybody related so that I can solve for one. It's up to you though. Like, let's say instead of getting your y and z in terms of x, like I just did for this last equation, let's say you're really a fan of the letter z. That's your favorite letter. Woohoo! So you let z be z, and then you try to set the lambdas equal to each other where you get x in terms of z and y in terms of z. And then when you have everybody in terms of z, you plug that into your constraint.
See, like, I know Lagrange is designed to circumvent the issue of not being able to use z. Like I suppose like the question behind the question thus becomes like what about any given shape prevents use of its z-axis in finding the other sides?
Okay, well, there's nothing that prevents us from doing that.
Wasn't it not fair?
I think that the question, if you're going to go back to the original question, you're going to have to read a book called Advanced Calculus by David Witter, where there actually is an example where if you do solve for z and you reduce the quantity to be optimized to a function of 2 variables, you end up with a wrong answer. You need to read that article, and then we'll have a conversation.
I'll make time.
Okay. I'm going to move on, and we can take further discussions about that offline. So let's do another example, because I got time, and I'm going to use it. So this example is a little bit trickier than the last couple that we've done, mainly because we're going to get a lot more than one critical point. And then we're going to have to use our brains to figure out who's the max and who's the min, if any, because it's going to turn out there's going to be a max and a min here, and you want to care about all of that. Okay? So this problem is kind of similar to the one where David was the astronaut in space, because we're going to have a temperature function. Let's say that represents the temperature in space at any point, x, y, z. And let's say the planet is this ellipsoid. Yeah, it's a weird shaped planet. It doesn't look like a sphere. It's a planet that has the shape of an egg. Cool. So what we're finding is we're going to find the max and min temperature on the planet that's shaped like an egg. And that's what we're going to go do. All right, so I'm going to use this approach that I've been talking about, this Lagrangian method, so where we form a function of 4 variables, x, y, z, and lambda, and you set that equal to the function that represents the quantity you're trying to optimize, in this case, the temperature. We're going to find the max and min temperatures, minus lambda, the Lagrange multiplier, lambda, times your g. Now your g here, you first want to get everything on one side and 0 on the other. So I'm going to subtract 144 from both sides. There we go. And then this junk that's on the left-hand side is my big G function. So now that's going to go into the parentheses here. And by the way, if you fail to do this step on your work, I will take away 1 point every time, because I want to see that step. Okay, and even if you use the show an example button version, you still have to get your big G represented by the general representation, where everything's on one side and Z's on the other, before you set the gradients equal to one's a multiple of the other. So now I'm going to go get all 4 partials. Yeah. Let's go get them. So this is similar to the other problem, and I like doing more examples just because that's what I'm about, and that's why we're behind other classes, because I take a lot of time. So Lx is going to be 8yz minus lambda times 32x. Set that equal to 0. Ly is 8xz minus lambda times 8y. Set that equal to 0. Partial with respect to z. 8xy minus lambda times 18z, set that equal to 0. The partial with respect to lambda is negative the parentheses 16x squared plus 4y squared plus 9z squared minus 144 equals 0. And this is the same equation as the constraint, if you multiply both sides by -1. Okay, now the technique where I have solve for lambda 3 times. Okay, so if I solve for lambda here, I'm going to get 8yz over 32x. And if I reduce this to lowest terms, because 8 divided by 32 is 1/4, I'll have yz all over 4x. So there's my number 1 lambda. And if I do the same thing for the second equation, I'll have lambda as 8xz divided by 8y. And if I reduce this lambda to lowest terms, I'll have lambda is equal to xz over y. So there's my number 2 lambda. Okay, fine. If I do this a third time, I'll have lambda equals 8xy over 18z. Reducing to lowest terms, I get lambda is equal to 4xy all over 9z. Here's my third lambda. Okay. Now, go use these lambdas and set them equal to each other, and do them in such a way that you get all the variables in terms of your favorite variable. Okay, as I mentioned before, just the way I roll is I let x be x, but I try to get y and z in terms of x also, so I could plug all that junk into the constraint and then solve for x. That's my goal. So when I do that strategy, I'm letting number 1 equal number 2 lambda here, so I'm saying lambda is equal to itself. Okay, fine. So yz over 4x has to be equal to xz over y. Yeah, that looks terrible. If I do cross multiplication here, I'm going to have y squared z is equal to 4x squared z. Yeah. Divide both sides by z, and I'll have, assuming z isn't 0, and I'll have y squared is equal to 4x squared. And then when you square root both sides, you're going to get plus or minus the square root of 2x squared. So I get plus or minus, oh, that's a 4, sorry. I'm thinking too quickly. Square root of 4 is 2. And so I'll get y is definitely having a relationship with x. Y is plus or minus 2x. Save that for later. If I set the first lambda equal to the third lambda, so I'm saying lambda is equal to lambda, I get that yz over 4x is the same as 4xy over 9z. If I do the cross multiplication thing, I'll end up with 9yz squared is equal to 16x squared y. Assume y is not 0 and divide both sides by y. So 9z squared is equal to 16x squared. And remember, I'm trying to solve it for z. So if I divide both sides by 9, and then I square root both sides, don't forget your plus or minus. So z in terms of x now is plus or minus 4/3 x. So good news, I have z and y both in terms of the constraint. So when I plug into the constraint, and the constraint is that big G function, I'm going to have 16x squared plus 4 times plus or minus 2x getting squared plus 9 times plus or minus 4/3 x getting squared, and that's equal to 144. And you guys know when you square something, whether it's plus or minus, you'll get a plus. So after cleanup, this looks like 16x squared plus 16x squared plus 16x squared I reduced, and that's equal to 144. And then combining like terms here, I get 48x squared had better be equal to 144. And then that's, I'm trying to solve for x now. So x squared has to be equal to 144 divided by 48. And then when I do the square root of both sides, and this is the part where you don't want to blow this with your plus or minus, you get x is equal to, by the way, this reduces to 3. 144 is evenly divisible by 48. Nice. Does that always happen? No. So we get x is plus or minus square root of 3. Now, folks, I claim that y, which is plus or minus equal to 2x, is plus or minus 2 square root of 3, and z, which is plus or minus 4/3 x, is going to be plus or minus 4 square root of 3/3. Okay, so we have x, y, and z. Now, how many critical points total do we have? Does anybody want to guess about all the different combinations of x, y, and z?
Two. 6.
Yeah, like
6.
we are looking at 6, right? Like I'm not counting wrong.
Never mind. It's gonna be 2.
I claim 8.
Oh, whoa.
Oh, right. It's 2 to the 3. Whoopsie. Uh-oh. Wait, no. Wait, yes, no. Wait, hold on. I'm not thinking right. No, I am thinking right.
Take a probability class, people. Now, look at the temperature function. Remember, the temperature function is 8xyz. So when is this going to be? So the question is, when you plug in, let's say everybody's positive. You know, x is square root of 3, and then that means y is 2 square root of 3, and z is 4 square root of 3. You guys know that a positive times a positive times a positive is equal to a positive, right?
Yes.
Yeah.
On the other hand, what if all of them were negative? Like a negative times a negative times a negative is what?
A positive. No, it's a negative. Jesus.
Negative.
Oh, no.
David.
Oh, no.
Please,
Oh.
think about this, okay? You get that if all 3 of them are negative, you're going to get a min. If all 3 are positive, you'll get a max. But there's other combos. So the max temp is when t is equal to 8 times x, which is square root of 3, times 2 square root of 3, times 4 square root of 3/3, and multiply all this mess together. And I get 64 square root of 3. And this is degrees Celsius, so this is like approximately 110.85 degrees Celsius, which is pretty hot. And this occurs at the points that, and these are all the 4 points that the max occurs. If all four, all four. Oh, sorry, I'm having real problems with my Surface Pro. Apologize. 4 squared. So that's one of the critical points that we get a max. But hang on, kids. What if x is negative, y is negative, and remember z could be plus or minus. So what if z is positive? Isn't that still going to be a
Oh, it's still a
positive?
positive. Oh, okay. So like,
And then what
Yeah,
if
because they're
x
being
is
squared.
negative,
that's
and then
cool.
y is positive, but z is negative? That's going to be a positive temp. And then what if x is positive, but what about if y and z are both negative? That's going to be a max. Now, what about the min temp? Well, the min temp is going to be just negative 110.85 degrees Celsius because it's going to have the same values for x, y, and z. But when does that occur? Well, that occurs at the other 4 critical points. What do you mean? Well, when everybody is negative, but what are the other 3 points? How about if x is negative, but y and z are positive? Won't that give you, when you multiply all these together, a negative number?
Yeah.
You see what I mean? Where you don't do the d-test to figure out who's the max or the min. You don't do the d-test. You do it by thinking about plugging your critical points back into the original function. Who's going to maximize him or make him the biggest, and who's going to make him the smallest. And that's pretty much it right there. Does that help?
Professor, how did you form the critical points?
How did I form the critical points?
Right.
Okay, let's go back to, let's recap what we were doing, and along the way we'll come into that. How's that?
Well, actually, I know how you got them, the whole Lagrange process. Like once you got the x's, y's, and z's, how did you mix and match them?
Well,
the probability thing.
because in this case, well, I don't want to get into probability theory, but when you have 3 things, all the possible combinations, if each thing can only be positive or negative, is 2 times 2 times 2 is 2 cubed.
Okay.
Now, and so I encourage you to take Math 119, which is a statistics class, George. And if you say, well, that's not part of my course curriculum, back in the old days when us engineers were at Cal Berkeley, every engineering program required all engineers to take a basic statistics class. And
It's still required.
And is it still required? It should be. Well, some schools deleted it.
Yeah, it's still required.
Trying to water down the
for all engineering.
But you should take a stats class because then you'll know the probability of all combinations,
Shout out
So
to Andrew Medine.
Andrew Medine, I believe, is retired.
Oh no, he retired? No way. Oh shoot. I didn't even get to say goodbye.
He's working part-time at different community colleges.
Oh man, I didn't even get to say oh man.
Okay,
Oh,
so let's go back and recap, and then we'll call it. Okay. Now, by the way, I haven't gone over some of the harder problems in Lagrange that involve finding distances, which we'll do Wednesday, as well as the technique. Sometimes this solving for lambda 3 times doesn't work, and I want to go over that Wednesday. So the recap is, you have a function that you're trying to optimize, max or minimize. You have a constraint. You form your Lagrangian big old function, which is your function to be optimized minus lambda, that's your Lagrange multiplier, times your constraint equation, where your constraint is written where everything on one side, 0 on the other. You get all 4 partials, you set them equal to 0. Then you solve the system. Now, the way I've shown you to solve the system is, solving for lambda every time. But let me caution you, that way it won't always save your rear end. If it does, it's nice. So I use this technique to find my other variables in terms of x's. I plug into my constraint. Now, this doesn't always happen, but if x is plus or minus a number, and then y is also plus or minus x, then, George, this is how we find, everybody can be one of 2 things, a positive or a negative. And then when you combine 3 things where everybody has a possibility of being positive or negative, 2 times 2 times 2 is 8. So that's how I got 8 critical points. And so then it turns out the max is where, you multiply everything together, you get a positive temp, and that occurs at 4 of the 8 critical points. And the minimum just happens to be the opposite of that, opposite temperature. And the 4 critical points that give the minimum are those guys, okay? So this is a hard problem. Sometimes the problem may not even ask you for all the critical points. I did like all the little details. Sometimes the problem, the way it's set up, they're like, hey, just find the max and min. And then you don't have to figure out all the individual critical points, George. I'm just talking to you right now. Sometimes they don't care. They don't even want that kind of detail. They're just like, what's the max and what's the min? And that's all we care about. And it's like, oh, okay, fine. Then you don't even want to know the fact that there are 8 critical points? Not interested. So it depends on the way they pose the problem, what they're looking for. Sometimes they don't even want the max or min. They just want the critical points. So please read the problem closely and figure out what it is they want and then give them what they want, okay? So I'm done. Thanks for staying. Have a good one. Congratulations if you actually understood today's lecture.
Professor,